in task 8. And here in task 8, we're going to do some fun stuff. This is about the buffer overflow attack that we talked about in the lecture. And we're going to use this to gain access to a remote system. And what it's going to do is demonstrate what we talked about, where we overwrite that buffer. And then when that happens, we're going to control the behavior. And then we're going to exploit it and gain access. So the gray note before we start is that in this task, we're using Parrot Security, which is our 1.13 machine, as the host machine. And the target of our attack is going to be a Vuln server on 111, the target machine. So let's go ahead and get that Vuln server up and running and started by clicking on Windows 11. And let me drag this to the other screen and bring Win 11 up over here. And I'm going to need to log in. I should just click here. And then I'll paste the password in and log in. There we go. Just went to the resources tab and clicked on the password rather than typing it in. Now what we're going to do is we're going to nav. By the way, just if you've just now logged into this, you'll need to, it says to restart the machine and then log in with admin password. So I have not done that. So I'm going to go ahead and do that. So let's click on this and we're going to go to the restart button and we're going to restart it. Here we go. So restart the machine. And so I'm going to let it restart. When I get logged back in, I'll join you there. Okay, so it looks like it's all restarted, and let's get back into the machine. Now we're going to go to step number 2, and we're going to navigate out to 6 buffer overflow Vuln server. So let's do that. So we're going to go to CH Tools, Mod 6 buffer overflow Vuln server. Okay, so what they want us to do is right-click Vuln server from right here and do a run as administrator yes. All right, so you see it says waiting for client connections, and there's a gray note that tells us that we would have to click yes, so that's fine. And now if it says that if there's a security alert, click on allow, which that didn't happen, which is good. And so now step 3 says Vuln server is running as shown right here. Yeah, nice. All right, so now we're going to minimize in step number 4, minimize the command prompt. I'm going to actually minimize Explorer also. Now what we're going to do is, let's open up Explorer back up. I forgot we have to get Immunity Debugger installed. So let's go back up a level and then go to Immunity Debugger. Okay, so we're going to right click Immunity Debugger and we're going to run it as an administrator with a yes. All right, and the gray note says click yes to proceed. And that's for the UAC. And now it says there is a pop-up that appears. Click yes to install Python. So there is Python right there. It's not the most up-to-date version, but that's good. We're going to have to accept the license agreement like it says in task number 7. All right. And now, and task number 8, we're going to follow the wizard and do the default settings. At the completion of the wizard, it says in number 9, we're going to click on close, and then there's an immunity debugger setup pop-up, and we're going to tell it it's okay to install Python. So let's do that. There it goes. And we close. And okay, and it's okay to install Python. Yes. In fact, I encourage you to install Python everywhere possible. Although, do you know that the C programming language is like 90% more, 97 or something crazy like that, more efficient than Python? So I just did a really cool little experiment on an AI. And I had it write the most compact C code possible. It was pretty amazing what I was able to get it to do. And I had it make a Pong game in surprisingly few lines. Either way, now what we're going to do is we have the setup, Python setup window. We already did the next for that. task number 11, step number 11, actually not task 11. After completion of the installation, navigate to the desktop. So I'm going to minimize that. And there's a desktop. And we're going to right click on Immunity Debugger. Let me get rid of this thing here. Right there. Okay. Right click on Immunity Debugger, run as administrator. And yes, I certainly do want to make changes to my system. Hey, that looks familiar if you just listened to the lecture or watched the lecture. If you watched the lecture, you saw that we went through lots of screenshots of Immunity Debugger, and you'll see this is exactly where we got those as we move along. So in step 12, it says Immunity Debugger window appears shown in the screenshot, but there's nothing in here. And so what we have to do is we're going to have to attach a process to it. So in step number 13, we're going to go to the File menu and attach. And you'll find that there are processes that we can examine here. And so in step number 14, what do you think we're going to select? Yeah, it's going to be that Vuln server right there. All right, so there we are with the Vuln server. And now we're going to click on Attacher. Attacher, s'il vous plaît. There we go. So now we've attached the process, and right now the process is paused. And that's what it says in step number 16, that it's paused. All right. However, in 17, what we're going to do is there is a run program icon that you'll see on the toolbar, and it looks like a regular run button, this little red button right here. And let's go ahead and click on that. And then you'll notice at the bottom right-hand corner, it says it is running. So keep your eye on that corner, because when we throw stuff at this Vuln server, we're going to crash it over and over again. And we're going to get the shape of what the registers are. And eventually we're going to be able to use that to launch an attack. So that's number 17. Step number 18. And that's where it tells you can note that the status has changed to a running. Step number 19, we're going to keep Immunity Debugger and Vuln server running. And we're going to switch over to Parrot Security. La Seguridad. Parrot Security Linux. And I'm going to type in Tor for which to log in. There it is. Very nice. And so now what we're going to do in step number 20 is we're going to use Netcat to establish a connection with the target vulnerable server and identify the services or functions provided by the server. We're gonna fill it out. We're gonna figure out what's going on. Now, what we're gonna need to do in step number 21 is we're going to open up a terminal, sudo suit, and then cd it in step number 22. So let's go ahead and do that. Sudo su tor cd. Boom! Quickly done, baby. So there it is. So now I'm going to do a clear, just so I have as much real estate on this terminal as possible. All right. Now what I'm going to do is run a netcat command. So we do nc for netcat, and then we have a -nv. So those are two of the parameters we're using. N means just give me IP addresses, don't do a reverse DNS lookup. V is verbose. And whenever you do these types of things in netcat, you can take all the parameters and squish them together. You don't have to put spaces between them, which I really like. Then we have to specify the target, which is 10.10.1.11. And then we need the port, so we put a space in there. The port is 99999. That means no. Hey, that's weird. All right, so now what we do is when we hit that command, we need to hit enter to execute it, and look at it talks to the vulnerable server. It says, "Welcome, welcome to the vulnerable server." And then you'll see that in step 24, it says the welcome to vulnerable server message appears. Type help and hit enter. Help. So we do a HELP in all caps. And there it is. It gives me a list of commands that I can run: stats, R time, L time, S run, T run, Gmon, Gdog, and many other commands. So those are the list of valid commands. That is what it says in step number 25. And 26, it says type exit and hit enter to exit the program. So let's type in exit and hit enter, and goodbye. We exit the program. So there we go. Netcat was able to communicate with it. But now we want to do some more communication. In this case, we're going to go to step number 27 and generate spike templates. And we're going to do spiking. And this is going to help us find out how this program breaks. So there's a gray note in step 27 that says spike templates define the package formats used for communicating with the Vaulm server. So we're going to define those formats. They're used for testing and identifying functions that are vulnerable to buffer overflow exploitation. So let's go find those functions. And what we're going to do is we're going to create a spike template. We're going to be using the stats function. So what we want to do is we're going to, I'm going to run a Pluma. If I can actually type in this window, Pluma, and that's our editor, and stats.spk. And by the way, when we're going through Linux, if you are a Linux expert, I mean, go ahead and get ahead. I'm doing this nice and slowly. 50% of my students are not that great at Linux. And so if you want to vi stats.spk, you want to vim stats.spk, you can do it, edit it yourself. This is your thing. So don't worry about following that as long as you know where to find it, how to edit it, etc. So I'm going to Pluma stats, and let me just make sure, I got everything spelled right. So it's going to come up. So now what we're going to do is we're going to put some of the functions in there. And what I'm going to do is I'm going to pause. I'm going to type them up, and then I'll give you a chance to type them up also. What we're going to be doing is the S redline function, the S string stats function, and the S string variable function. So let me get this typed in, and then I'll join you in just a moment. What we start with is the read line in this script. And what this does is it reads a line of input from the application. So this was going to synchronize the fuzzer with the target by waiting for a specific response before going to the next payload. And then we have S string stats. And don't forget right here between the S and the quote, for those of you who aren't good at this type of scripting languages, there is a space there. So what this function does is it sends a static string, stats, that what you see in quotes there, to the application. So that's going to be the Vaulm server. And then this space that you have to have after stats is actually important because it separates the command from any other data that might come after it. And so this is very important when we're sending specific commands to our target app. And then this third one down here, the S string underscore variable. What that is it's a function that sends a variable string to the target application, so that the 0 that you see there is going to really be there to indicate that the variable's name or identifier. It's going to identify that variable. So in the context of what we're doing, we're fuzzing, right? So this variable string is going to inject different payloads or maybe inject different data or stuff like that to test how the target application will work depending on what inputs we put in it. So we combine them into stats.spk. So it's going to read a line of input from the target app to make sure it's synchronized. It's going to send the command stat space to the target app. It's going to send a variable string, which can be different payloads, to the target app. We're going to test its response, and we're going to find its vulnerabilities. So that's what we're doing with this little script. So just FYI, and this is something you can look up if you want more information on. So we've saved it, which is step number 30 and 31. And once we save it, we're closing the editor. So let's go ahead and close it since it's saved. There we go. Okay, so now we go to step number 31 in the terminal window. We're going to use this Spike template, and we're going to send commands using this Spike template to the Vuln server. So let's do a generic underscore send underscore TCP. We're doing that to 10.10.1.11. port 9999 stats, which should be in this directory, .spk, 0 space 0. So that is what we're trying to do. We're trying to, that generic send TCP, that's the actual Spike utility we use to send the fuzz data over that TCP connection. It's going to read the script and generate the payloads. Obviously, the target is 1.11 and it was port 9999. And then we're taking the script that we ran and we're going to run it through that script that we just did. And the 00, these are two different parameters. One is called the skip var, and the other is called the skipster. So skip var, and then the other 0 is the other variable skipster, skip str. And what they do is they control what variables or strings to skip during fuzzings. But we have this whole thing set to 0, so we're not skipping anything. So it'll fuzz all possible inputs. So we're going to establish that connection, run that script, and get that fuzzing all running. So let me click on go, and there we go. Fuzzing is taking place. So what's going to happen is we're going to leave the script running, and then we're going to head back to Win11. And you'll note that the command, none of the fuzzing has broken it yet, right? It's still running. And so we see that the process is still running, at least for now. And that means that the stats function is not vulnerable to buffer overflow. But maybe another function is vulnerable to buffer overflow. I mean, look at that. We're testing stats. We're throwing all kinds of stuff at it. And stats isn't breaking. So maybe we could do the same thing with the trun function. So let's go back to Parrot. And we'll Control C out of our fuzzing. So we're out of it. And that breaks the script. And step 36, we're going to go back to Pluma. And go back to, actually, we're going to do a new one called trun, because we already did stats. All right, so there's our trun.spik. All right, so now what we're going to do is we're going to put in some of the same stuff like I described earlier, except for we're going to look at the trun. We're going to look at the trun function instead of the stats function. So let me type this in, and then I'll join you when I get it typed. Hopefully you got it typed in. I'm going to go ahead and save this, but there we go. Don't forget to leave that space after trun. And so what is it that we're doing? So we tried the stats, and now we're trying trun. Stats and trun, they're both functions that are commonly used when we're fuzzing. They're very common in this type of activity. The stats function is going to use to send specific commands to the target application and then fuzz the input. And what we want to do is see how it handles like repeated subsequent inputs. So we would, like we just did before, following it, all these different payloads that we send at it, right? So the trun function is used to test for these buffer overflow vulnerabilities by sending large amounts of data to the application. So what we do is we send these large amounts of data, and then we can see how it handles large inputs, or if it crashes, and that would tell us it's a buffer overflow. So those stats and trun are commonly used functions, but there's also the user function that we could put. It's the exact same thing, except for you would create user.spk, and that would be for user authentication fuzzing. The pass a function, and exact same thing, except for you put pass where it says trun in there for testing password inputs, and the get function for get requests on web servers, post, auth, list. Those are the only ones I can think of off the top of my head. But anyway, those are some of the functions that we might test. And so now we're going to start working on that trun function to see what we can do with that those large chunks of data. So now it's time to run it. And so what we're going to do is on step 38, we saved it. Step 39, we're going to run that spike template. Here we go. So I'm going to go back up to here, and I'm going to change this from stats to trun. And so we're going to do a generic send TCP, 10.10.111, 9999. I don't know, I got rid of one of those nines. Here we go, throw that back in there. 9999, trun spike 00, and that should do it. And so we're going to go ahead and run it. There it goes, like a fuzzing. All right, you can see if you look closely, the number is increasing. So we're going to leave that script running as it says in step 40, and we're going to move over to Windows 11. Whoa, dude, check it out. It is paused. So we can see that the process, the status is paused. So the trun function is vulnerable, and in that vault server, vulnerable to buffer overflow. So in step number 42, spiking the trun function has overwritten, and it tells you the stack registers over here on the upper right-hand side that were overwritten. And you'll have to look at yours. The font is very small here, but you can always zoom in on your own lap. Also, in these windows, you can right-click and go to Appearance and Font and give it a different font. So I don't play with that a whole lot. I guess I could experiment with it offline, but normally I just keep the font the way it is. It is like also you saw in your courseware. We'll leave that the way it is, but I can see, just looking at it, it's an EXSP, EBP, and EIP. We're talking about this during the lecture anyway. And in step 43, you can observe the top right-hand corner where the ASCII value written is ah. So all those A's that you see right there. So now what we're going to do is we're going to go to step number 44, and go back to Perro Sécurité and do a Control Z. Control Z. Yes, you Americans. That's the correct way to say Z. All right, so we're back here now in step 45. After identifying the buffer overflow vulnerability at the target server, we need to perform fuzzing. Fuzzing, so we did that spiking, and now fuzzing specifically is performed to send a large amount of data to the target server so that it overflows the buffer and overrides the IP register. So in step number 46, we go back to Windows, and we're going to close Immunity Debugger. Bye-bye, Immunity Debugger. And the vulnerable server process. So that's closed now. Now what we're going to do is we're going to relaunch the Vault server process and Immunity Debugger. And so let's do that. So let's go back over to Vault server, and which is going to be up and over here. And we're going to right click, and we're going to run as administrator. Since we did crash it pretty much, we crashed it. Then we're going to go, and what I'm going to do, I think, since a couple of times we might revisit. I'm going to create a nice little shortcut here. And then we go to Immunity Debugger. Actually, I probably don't need to do that since I've already installed Immunity Debugger. And run it as administrator. And then we're going to go to File, and we're going to attach. And we're going to attach that Vault server. All right, there it is. And so now that we've attached the Vault server, we need to run it. There we go. And now it is running again. Now what we're going to do is go to Perron Sécurité in step number 48. And what we're going to do is minimize the window. And after we minimize the window, what we're going to do is we're going to go to the network. So let's go to Places. And in Places, what we want to do is we want to go to the network, which is right here. And in the network, what we want to do is do a Control L. I can do that on my keyboard. And what we're going to do is we're going to go do a SMB : 10.10.1.11, hit enter. And then we're going to be using administrator. Tab down a couple of times. Password is capital P A $W0RD. By the way, it tells you all that stuff in step number 51. So once we do that, oh, I'm sorry, it's admin. ADMIN. I have an excuse. I'm doing this lab like late at night. So yeah, that's my excuse. So what we want to do now is double click the CH Tools folder. There we go. All right, we're in the CEH Tools folder. And now what we're going to do is go to Buffer Overflow and module number 6. Module 6, Buffer Overflow Tools. And the scripts folder, we're going to right click on it and copy it. If you look inside it, you get lots of cool scripts. So we're gonna copy that, a script folder. I'll go ahead and close this window. And then what we're gonna do in step number 54 is right click right here on the desktop and paste the script folder. Bada boom, there it is. And you can prove to yourself that it's the right folder with all the stuff that's in it, which I always like to check everything I do. All right, so now what we're going to do is we're going to run a Python script to perform some fuzzing. So we're going to switch to a terminal window, and we have one right here, already ready to go, just down here on the, what in Windows would be called the taskbar. And what we're going to do is we're going to do a CD, and we're going to do a /HO tab, /ATT tab, D tab, ES tab, there we go. And then SC tab. So that takes us to scripts, and we're going to be in the scripts folder. If we do an ls-l, there are all of our scripts nice and organized, and gives you all their nice permissions and etc. Now we need to do a little chmod. So to make sure, if you notice, there are no executes on there, only writes and reads. So chmod +x, and we'll do fuzz.py. And now let's do a double up arrow in LSL, and we should see that fuzzpy is executable if I did it right. So chmod +x. Oh, -x. What a bad typo. Yeah. Okay. So I'm glad I actually went and looked at that because I did a -x. All right. So now let's do a double up arrow. And then Alice, there's the X I was looking for. Yes. I would have just typed that blindly and got myself in trouble. I did a minus instead of a plus. Mars rovers have crashed for less than that. All right, so now we're going to run it. So we're going to do a ./fuzz.py and get that typed in over here. I'm in the wrong context. There it is. So once we do that, when you execute this script, their buff multiplies for every iteration of a while loop and sends the buff data to the vulnerable server. So that's what FuzzPy does. In fact, if I go back to Windows 11, it should actually not say running anymore. I'm surprised it's saying running because it should be totes crashed. At the bottom right hand corner, it should say paused. And so I'm not sure why it doesn't say paused, but it is. There, look at that. Thread, and it gives you the terminated exit code 0. So it should say access violation though. So I really want to set this up one more time. So let me just pause the recording and set it up just very quickly and make it work the same way. And it is paused. Woohoo! So now I'm matching the lab. I really think that when I did my attach, that I attached to the wrong process. That's what I think happened. So now we go to step 61. The top right window, we can see over here the EIP register. We lost the EIP register. It's overwritten by that script. That's step 61. 62, we go back to Parrot security. And we can see here we're still fuzzing. We can do a Control C. All right. To stop it. And so in step number 63, a message appears. And it's saying that the vulnerable server crashed after receiving approximately 10,200 bytes of data. Niet. That is not what happened to me. Niet. It was actually, for me, it was 6,700 bytes of data. And the gray note says the byte size may differ in your environment, which is absolutely true. Okay, so now we're going to go back to Windows 11 and step 64, and we're going to close Immunity Debugger because we crashed our program. Now we're going to relaunch them both, and attach the Vuln server, and run it. So that is all in step 65. So let me do that real quick. So let's start the Vuln server as administrator. Yes. Looks like it's running to me. We're going to go to Immunity Debugger and go to administrator. We should run it as one. And then we're going to go to the file menu and attache the Vuln server process. Make sure I get the right one this time, and then attache. Now we need to run it. Run the program. And at the bottom right hand corner it says running. So in step 66, it says through fuzzing, we've understood that we can overwrite the EIP register with 1 to 5,100 bytes of data. Yeah, and sometimes you have to fuzz a couple of times, but either way, a few times sometimes. But we have some data about how to crash this program and where it's vulnerable. Now we're going to use the pattern_create Ruby tool to generate random bytes of data. And we go to step 67. We're going to click on Parrot Security. That same machine we've been using. We're going to open up a new terminal window right over here. Okay, and we're going to sudo the terminal window and tore it up. So sudo and then hit enter. And, it's not. Yeah, okay, here we go. That's better. Okay, so there we are. And now we go to 69 and we're going to do a CD. Get back to that root. And once we get there, we're going to head over to that Ruby tool, pattern create. So what we're going to do is do a slash. We're going to run essentially that tool by doing a /usr share meta. So that's going to be Metasploit dash framework. I'm sorry, I'm trying to tab complete it and then have to look over at the monitor. So I'm going to pause and type it out. And since it's so hard to type and look at the monitor at the same time. Okay, so yeah, that command that we just typed in, it's actually a very important command. We're using Metasploit, obviously. And just like I was talking about in the lecture, we're trying to generate a unique pattern at a specific length. And so it's used to identify the exact offset. We're talking about that in the lecture too, where the buffer overflow occurs. So when we have this over here, the USR share Metasploit framework tools exploit pattern create Ruby, the script is that Ruby script in the framework used to generate those a huge number of non-repeating patterns of letters. And then that -L flag way over here on the right side here, it's going to give us the length of the pattern that's generated to 10,400 in this case. And so the pattern generation, we're going to have a unique pattern of 10,400 characters, sequences of characters that don't repeat, and that makes it easier to find the exact offset where the buffer flow is going to happen. And so we're going to use this to do some crash analysis using Immunity Debugger, and then we'll be able to find the pattern offset. So that's what we're looking to do here. So let's go ahead and hit enter. And there, look at that. Look at all those wonderful characters. So that's good stuff. So now, as you see in step 71, it'll generate random bytes. Right click on it and copy the code, and then close the window. So let's right click on it. And I think I'm going to need to select that, not just right click on it. Oh, and maybe that worked. Whoa. So there it is. Okay, so let's try it again. Yeah, so I need to select it all. So let me full screenize it. And I'll start way down here. And we'll go all the way to here. And now I've copied it. Okay, so there we go. So now what we're going to do is go to step number 7. It says close the terminal window. I'll go ahead and do that. You can always recreate it if I needed to. And go ahead and close the window, close the terminal. And now what we want to do is we go back to the window that we had open previously, which is right here. And what we're going to do is we're going to run a Pluma command to create a file called find off.py. So find off.py. So FINDOFF or find offset. Once we get into Pluma to edit this file, we see that there's a script, and there's some the offset they have right here, the AA, all that kind of stuff, right there. What we're going to do is replace what we have with that. So what it says specifically in step 73, a Python script file appears. Replace the code within the inverted commas in the offset variable with the copy code. So this is the offset variable, and it's within the quotes. So what I will do is this is offset. It says offset B equal B quote, right? So I'm going to do that. I'm going to put in the B quote myself. So offset equal B quote. So that is how it should look. So offset equal B quote. And we still have everything else. Nothing's changed. That's good. 1011 is good. 9999 is good. Good. All right. So that looks good. It says hit Control S to save the script and close it. So let's do a Control S as in save. And then we'll close it. There we go. So now that we've done that, what we're going to do next is we're going to do a chmod plus x. Chmod plus x is going to be for find off dot py. We hit enter. There we go. So we've just made it executable. Now we're going to run it right here. So we're going to do a ./findoff dot py. And boom, look at it. Dump that. Syntax error. Terminating string label. So let me go back over here. There might be that I didn't get the back quotes. Yeah, I think that's why. Okay, so I edited it, pasted it, and that's better. Look at that. All right, so it ran. I got the quotes wrapped up in the wrong place. So now that that is done, what we're going to do now is we are going to, that was step number 76. And so what it says is a gray note is it sends random bytes of data to the target vulnerable server, which causes the buffer to overflow the stack. And so that's what it should be doing. So let's go to step 77 and go to Windows 11. And sure enough, in Windows 11, we see that the machine is paused. It crashed it. So in the immunity debugger window, we can see, there, look at that. Look at that. That we see ESP, EAX are overwritten, and EIP. The EIP register itself should have that. Looks almost like a hexadecimal number in it. So that's good, right? So we can see it's overwritten with random bytes. So what we want to do is note down those random bytes in the EIP register to find the offset of those bytes. So I'm going to pause real quick and make a note of that. So, by the way, you can just double click on that and copy it. And I copied it. It's 386 F beat. So that's very easy to note down. And I did. And that's good. So now what we're going to do is go to step number 80 and go back to Parrot Security. And in a new terminal window, we're going to sudo su. So I should probably get rid of this terminal window. Thought I might need to reuse it again. And I could probably get rid of this terminal window, but I need to leave this one open. So let's go to a new terminal window. And so we're going to sudo su it and cd it. So all right, there we go. So now we're ready for it. And now in step number 83, we're going to get ready to run yet another Metasploit command. So let's get that typed in here, and then I'll talk to you about what we're doing. So we're going to do usr share Metasploit framework tools exploit. And under exploit, we're going to do pattern underscore offset dot Ruby. And then what we're going to do for the length dash L is we're going to do the same one, which is 10 400. And then dash Q is going to be that number that you copy down. So it looks like it's the same thing as it was for that we got for the lab. So it's 386, and then we're using F beat. Well, that's leet speak. So 4337. So 386 Frank 4337. So 386 Frank 4337. Okay, I wrote that in correctly. All right, got that done. And so this command, let's talk about it just a little bit. Again, we're finding the offset, right? And for a specific value, and that's the number we typed in. And so the command out to the same thing, pattern offset Ruby, Metasploit, and the length flag, we already talked about that. The Q is the query value. And so we're going to find the exact position of the value 386 franc 4337 with a pattern length of 10,400 characters. And so it'll help display the offset where the buffer overflow is going to occur. And so that's what this command in specific does. So when we run the command, we should get back a number. So here we go. Boom, baby. Exact match at offset 2003. And so what it says in step 84, as the result appears, it says that the EIP register is at an offset of 2003 bytes, as you see right here. So that's good. So now that we know that, we can use that. So we're going to close that terminal window. Okay. And then we're going to go back to Windows 11. We're going to close the Immunity Debugger. And we're going to relaunch the vulnerable server. And that's what we do in step 87. So bye-bye, Mr. Immunity Debugger. I'm sorry, but I cannot grant you immunity. You have to be tried as an adult. Here we go. So we're doing that. We're going to run Immunity Debugger. Debug everything. All right, there we go. All right, now we're going to go find that vulnerable process. Oops, that's not it. Don't want to get the wrong one there. Vuln server, attach. And then we're going to run the app. Bottom right hand corner, it now says it's running. And so now what we want to do in step 88 is we're going to run a Python script and overwrite the EIP register. Step 89, we go to Parrot Security. And in the terminal window, we're going to overwrite.py. So what we're going to do is we're going to type in chmod plus x, not minus Kevin King, overwrite .py, hit enter, and that's better. And so now we're going to do a / overwrite.py and hit enter. All right, there we go. And that was pretty quickly. So what we're going to do is check and see if we can actually control that register. So we know that's the EIP register we're dealing with, but can we control it? So in step 91, we switch back over to Win11. And sure enough, we've crashed the program. And the EIP register, sure enough, is overwritten. Look, you see there, life, the universe, and everything. 42, 42, 42, 42. So it can be controlled. It can be overwritten. Nice. So what we're going to do is close that Immunity Debugger. And we're going to relaunch it and attach and run that Vuln server again. So let's run the Vuln server as an admin. Tell it yes. Run Immunity Debugger as an admin. Tell it yes. Let's go over to File, Attaché, and find that Vuln server. There it is. Attaché. And then we're going to run it. So now the app is running. And that was step number 93 in your lab. And now what we're going to do is almost the pièce de résistance. We need to find out if there's anything that we will do that will harsh our buzz. We don't want this to not work. So in step number 94, before injecting shellcode into the EIP register, we must identify bad characters that could cause issues in the shellcode. And so you can get those through a Google search. We talked about these before. No byte, 000. Those are bad characters. But anyway, let's go ahead and do it. We're going to go to Parrot Security, Linux, in the terminal window where we have another chmod that we want to do. So chmod plus x. And we're going to run that against bad, oops, I have to type that right, AD, bad characters, PY. And then we're going to do a /, and we're going to run it. And this one here, we talked about during the lecture, is one that will find out if there's anything that we need to know about before we run this. So here we go. Bad characters, pi, bad cars, and nothing shows up. So that's good. So now what we want to do is we sent those bad characters along with the shellcode. And now we can go to Windows 11. And what we should find is what characters there were. So let's go ahead and switch over to Windows 11, as it says in step 9.7. And then what we're going to do is in the Immunity Debugger, we're going to go to the ESP register. If you look at the ESP register, which is right over here, click on it, double click on it. You can just select it. You can see it turns blue. And then you right click on it. And then you go follow in dump. So down here, you see that we get the dump from that value. And that's in the left window. And so what we see, if you go through here and look at the dump, just like I was saying a little bit earlier, there are no bad characters that cause problems in the shellcode. And so, yeah, so yours might look a little bit different, but look at that dump. You don't see any bad characters. And so this is going to go off without a hitch. So let's try it out. What we're going to do now is close Immunity Debugger and the vulnerable server, which is closed. We're going to restart the vuln server, and we're going to restart Immunity Debugger. Move this little guy out of the way. And there we go. Run as administrator. Yes. We need to attach it. Let's do that. And then we go over to the vuln server. Yep, we got the right one, and attach it. And then we're going to run it. Right, and all of that is step number 101. Relaunch Immunity Debugger and the vulnerable server as administrator. Now attach the vulnerable server process to Immunity Debugger and click Run Program toolbar to run it. Now in step 102, we need to identify the right module of the vulnerable server that's lacking memory protection. So in Immunity Debugger, you can use scripts like MonaPy, like we talked about in the class. So now what we're going to do is navigate. So actually, I think I'll open up another folder so that I can always go back there if I need to. So I'm going to open up Explorer and go to Windows and CEH Tools, module number 6, System Hacking. And what we're going to do is go to our buffer overflow, and we have scripts. And those are the scripts we're talking about. And let me just go ahead and do this to make them easier to see. There they are. And so now that we're here, we're going to copy MonaPy, and we're going to paste it in the debugger py command. So there is, where's Mona? There's MonaPy, right? A copy. So copy MonaPy, and we're going to paste it into C program files, x86, Immunity Debugger. So that's going to be under Immunity Inc., Immunity Debugger. And under Immunity Debugger, we're going to go to py commands. And in py commands, we're going to right click and paste it. And you'll need admin. Yep, I've got it. Boom, baby. Look at that. MonaPy fits right in to our py commands in Immunity Debugger, right? So, and there's a gray note that talks about the access denied pop-up, and we continued through that. Now, 104, step number 104, we're going to close this nice little window here. We're going to switch to the Immunity Debugger window, and you'll note that the program is still running, the app is still running. So what we do is at the bottom of the window, there is a white band. It's actually a text field. And in that text field, what we're going to do is bang. So exclamation mark in hacker speak, we call it a bang because it takes too long. It's entirely unreasonable to say exclamation mark. We could just say bang. So we're going to type in bang Mona modules. So bang Mona or exclamation mark Mona modules. And then at the end of that, you're going to hit enter. And I did type in something incorrectly. I left out the bang and I was talking so much about it. Now that works. Great there, mate. I was sure I typed in that exclamation mark after talking about it so much. So anyway, what you can do is you go through here and you'll find as you pour through this, and I wish we had time to go through it. I talked a little bit more about it in the lecture, but what we find is there's no memory protection for the module ESS function or funct.dll. So that's what we're going to focus on. Very simply, if you look at right down here where the module info is, and you look at all the different memory protections that you can have, ALSR, etc., and for ESS func right over here, it's false for all of those possible memory protections. So that's how we know in this area. So that's actually good for a hacker. So that's very good. We can hack that. So now what we're going to do is go to step number 108. We're going to exploit ESS func DLL to inject shellcode and take full control of the EIP register. So let's go to step 109 and click Parrot Security. We're back. We are back. Large and hopefully in charge very soon. And so we're going to open up a new terminal window. Why? Because the old one just won't do. And now what we're going to do is we're going to sudo su it and cd it. So let's do that. And take us up to the top there. And now we're going to be in step number 112. And now we're going to run the converter.py command. So let's type that in. And what this does is it just converts. And you'll see this. It's going to ask for assembly code as input. So let's get ready to do that. Do Python 3. Oops. Let me clear it again. So Python 3 /home attacker converter py. So there we go. We typed that in. And it says enter assembly code here. So what we're going to do is we're going to enter JMP, ESP, and yeah, actually just those two. So we enter both JMP and ESP, and then we hit enter. It's going to ask us, it's going to give us the hex, which is for FFE4. So FFE4 is what we're looking for. That is the actual result that it converted that information to. So now that we know it's FFE4, where you can close this terminal window. Nice. And then we go back to the Windows 11 machine. And in the Immunity Debugger window, we see it's still running here. And now that we know we have FFE4 as the exact location for this module, we can go back over here to the little window down here, and we're doing a bang Mona again, so that we have exclamation mark there and find -s. So we need to find this out, and that's going to be quote slash, actually that's a backslash, XFF / XE4 quote. There we go. So that is what should happen. So what this does, if you have a look at it real quick, is it will take advantage of that plugin, and we're going to search for that specific sequence and that specific module. And so that's why we have the Mona find. And the Mona plugin, this command looks for the specific patterns, sequences in memory. And that's that -s. And then we have the /XFF. So the S is the search string, and the string is the XFFXE4. And that's the byte sequence to search for this particular sequence that corresponds to the JMP ESP instruction if you're dealing with assembly language for an x86 processor. And this is very commonly used in buffer overflow exploits against that execution stack. All right, so now let's do the rest of the command, which is a -m. And we're going to type in ESSFUNC.DLL. All right, so now we have the entire command typed in. And so the -m is the module that we're going to search for, that byte sequence. And then the ESSFUNC.DLL is the target module. So let's hit it. Nice. I think that's good. All right, so let's have a look and see what we got. And yeah, that's good. We found a total of 9 down here in the red. And so what happens is we have a return address of a vulnerable module. And you can see this return address right here. It's a little bit small. This blue line right here. There it is. Hard to see. But the vulnerable module right over here is 0x625011 Alpha Frank. So AF. Wow. A lot of work to get there. A lot of work to get. So let's go ahead and close Immunity Debugger. And that's step number 119.120. We're going to launch it, that and the vulnerable server, and run it. So let's go back to Vuln server, run as admin, and get everything running. So let me just do that. Got that. Right click on that. Go there. Hit yes. That is odd how it rearranged itself. Wow, that's cray-cray. So anyway, I'm going to still do my attach. And we will attach Vuln server. And let me see if I can get the windows to cascade, just like that. Arrange icons. Oh, let's try tile horizontal. Hey, that'll work, actually. I like that. Tile vertical. Interesting. So what I need is my Immunity Debugger. I need my registers. A callback thread. There's my CPU thread. Call trace. References. There's my call stack. My breakpoints. Memory map. Log data. No, actually, this is going to work fine. This is going to work fine. But let's go ahead and run the app. Yeah, you can see it running right here. This will work fine. It should not have done this, but it did. And it's not, whenever I use Immunity Debugger, periodically something like this happens. And what you have to do is kill some of the windows that you don't need and then go ahead and rearrange the icons. But I'll take it for what it is right now. So what we're going to do is we have Vuln server running in Immunity Debugger. And now what we want to do is go to, actually, you know what? I should probably not have it running. So let me stop it real quick and bring it back in. Okay, so I reattached it, but I did not hit this run button because there's something that we need to do. and we need to disassemble. So I'm going to go ahead and click on the disassemble icon. And once you do that, you're going to get a little pop-up window. And what we want to do is enter the expression that we got last time, which is going to be 625011 Alpha Frank AF. So 625 011 AF. All right, now once you get that into our expression that we're going to follow, we put it in here, you'll see that it goes right into our CPU thread section here. And we get pointed at that ESP function, and what we do is set up F2 to set a breakpoint at exactly 625011 AF ESP. So let's do that. And then once you've selected it, you might be able to see a little bit better here. That one way at the top. Then you can hit F2, and just to make sure because I have all these function keys and so on, and especially if you have a Mac or something like that, what you can do is you can hit the virtual keyboard and then hit the F2 from the virtual keyboard. And you'll see that it sets up, it selects it. And when it selects it, that's setting the breakpoint, which is what we were trying to do in step number 1, 2, 3. Now in step 1, 2, 4, we're finally going to run the program. So let's run the program. As you can see, it's running. Now we go to step number 1, 2, 5. We'll go back to Parrot Security. There it is. Looks normal. And we're going to maximize the terminal window. So let's do that. Hit that green button. Very nice. And what we're going to do now is we're going to do that chmod again with a plus X for jumpy. I like calling it jumpy. JUMP dot PY. Right. So let's do a chmod there. And then we are going to run JumpPy. And we talked about this in the lecture, but this is the one that does the jump. And so let's do the ./JUMP and enter. Boom, there it is. Okay, so now what we want to do is that we've executed the jump Python script. Let's go back to Windows 11. And in Windows 11, in the debugger, we'll see that the EIP register has been overwritten with the return address of the vulnerable module. And there it is right there. Look at that. See, exactly. Even ending in the Alpha Frank. So you can control the EIP register if the target has modules that don't have proper memory protection. Great. That works. So we close Immunity Debugger. And in step 131, we're going to relaunch the vulnerable server as administrator. This time we don't need the Immunity Debugger. We've figured everything out that we need to run the hacks. So here we go. So now we're running that. Now we switch to Parrot Security. And we open a terminal window. With a sudo, su, and a cd. All right, now with that, we go to step number 135, and we're going to type in another MSF Venom, and we know exactly what we need to do with this. And so this is going to be one where we're going to get a shellcode to be generated based on a specific payload with a -P and on a specific listening port 4444, specific file type architecture in bad characters. So we're going to be typing in the command, here we go. The command is MSFNM. And we're going to type in -P for a payload. And we're going to do a Windows /shell. And here it is. So if you look at what this is, obviously we're running MSFNM, and where we see that P, that's just for the payload. That's going to be a Windows shell _reverse _TCP. So reverse shell, sending that back through from the target to us. It's going to generate a payload for us. And we see the L host, which is us, 13, and the port and the exit function. This is where the payload finishes running. It's going to execute, right? If we set it to the exit function to thread, what happens is it will do a clean exit to help even avoid crashing the target app. And then the -F that you see right over here is a flag that does the format of the output. In this case, we're formatting it in C. And that A is for architecture. So the C, when I say C, that's the C programming language. And then the A for architecture is the x86, which is going to be a 32-bit architecture for Intel. And, or actually, x86 can be a non-Intel to AMD. And then -B over here is for the bad characters to avoid. And we're doing a \x00, which is null byte. So avoid null byte. So overall, what we're going to do is generate a reverse shell payload in C. Will be embedded in a C program. And we'll see that in just a few moments. So that is what we're doing. Let's see to it that this works. I'm going to click in here. Oops, there we go. And now let's run it. And so what should happen when it executes is we should see a bunch of code. So let's go ahead and let's go for it. Generating. Boom, baby. So that's how it should look if you typed it in correctly. I'm trying to go over each section so you make sure you type it in the way it should be. I have so many students who mess up on this, and it's good not to. So what we're going to do is select the code, right click, and copy all of that shell code. So that's going to be, scroll up, and oops, there it is. Let me go grab that. Try it from the bottom. Might be better. And we'll copy that. All right, so once you copy that shell code, what we're going to do is we're going to go to shellcode .py, and we're going to put in all that stuff from the XD9 all the way to the end. So I'm going to minimize this just in case I need to go get it again. So what we're going to do is we're going to Pluma shellcode.py. And see there it is. We already have another code in there. And what we're going to do is we're going to replace that code. So in step 141, we're going to replace the shellcode that we just copied over this shellcode. So what I'm going to do is I'm going to select, actually I think I have quotes already. So I'm going to select all the way through here and the quote. And I'm going to do a Control V. And I just need to make sure that it has quotes at the beginning and quotes at the end. And it should terminate that line in a semicolon. So that's how it should work. Okay, so in step 141, it says type the B in the beginning of every line to convert strings to bytes. So now what we need to do is copy that B at the beginning of every quoted line. So I'm going to go ahead and do that, and then we'll compare when I'm done. Okay, that was a lot of typing, so I just had my intern do it, and I went out and watched some Netflix. Just kidding, I don't have an intern. And I don't even watch Netflix, so it's all good. So now it's time to save this. It has to be perfect, so make sure it's perfect. I checked over, especially at the ending. I did not paste it correctly 100% at the ending. So I had to go back through and change that just a little bit to make sure that I ended with I think I left some of their stuff in there. All right, so now that is done and it's been saved, now it's time to run it. So that's step 142. So it says now before we run the command in step 142, we're going to need to run netcat to listen on port 4444. So let's go ahead and close this Pluma. There we go. And oh yeah, I can close this too. That's actually what I was trying to close. Okay, there we go. So now what we're going to do is open a terminal window. So we're going to open up a new terminal window. And we're going to sudo su and cd the terminal window. There we go. And now that's step number 143 and 144. We're going to run that netcat. So we're going to run an nc. And so this netcat command has some other parameters than the other netcat command. Because what we're going to do for this netcat command is we're going to use -n VLP. And so with the NVLP, we have several things going on. Number one, the N that we see here is for no DNS resolution. It's just the IP address. V is for verbose mode. L is for listen mode. So it's going to be waiting to accept incoming connections. So your machine essentially is like a server just waiting for clients to connect and port 4444. Let's put that in there. All right, now we can hit enter. And it's just listening. And so that's so the special part of that was L for listen mode. Now, as we get deeper into these labs, I'll stop explaining what everything is doing because we're going to be using a lot of this stuff over and over again. But now the netcat listener is set up. And now we go back to the first terminal, which is not that one, but this one. Here we go. And now what we want to do is we want to go to the shell code and execute it. So we're going to do a chmod +X, and we're going to hit shellcode. Where's my shellcode? Shellcode.py, and there it is. So there we have made it executable, and now we can run the shellcode. Now this is the most important one. We're actually going to upload the shellcode. Now there are some steps that we could have done to make that we have done, and then others that we could have done. But anyway, let's go ahead and run it. So we're going to do /shellcode.py and run it. So now that we've run the shellcode.py, we've run our essential hack. So we go back to the netcat listener terminal, and boom! So nice. So we see now we have a terminal that is from the target machine. Isn't that cool? So we type in who am I? Who am I? All right, I am admin. That's not a bad account to have on a machine. I think I can take that. I can do let's see if I do a dir. Look at that. I get stuff. So I'm on this machine. So anyway, bottom line is it worked one step at a time, and we did it. hopefully you're still with me. Hopefully you did it also. Hopefully I've actually had the record button on while I was oh no, I'm not recording. No, actually I've been doing a good job at that. So that's it. Step 151 concludes the demonstration performing a buffer overflow attack on a remote access system. So we can close everything, and we're going to need, just remember for this one on step number 153, you need to restart the parent machine because of all the stuff that we just did here. What I always tell students, this is the end of this task, but we have more tasks to go. So one of two things is maybe not just restart the parent machine, but maybe actually restart the lab, get your time back and everything. It's doable. It might be worth it. So now what we do is we go over to Windows 11, and we're going to restart that one also. And so here in Windows 11, click on that thing, restart that also. But anyway, we're following the lab. Now, at the end of this task, there is only one question that you may answer if you would like. And then get your score before going on to lab 2. So you have now completed lab 1. Pat yourself on the back if you have the flexibility. If not, have a friend do it. So anyway, that's the end for this lab. And we'll see you in lab number 2. Salut. Tout à l'heure. Bye.